Hello, people. So, this talk, somewhat different from last talk. So I will start by encouraging you to ask questions as we go along, because this is a talk about last year's worth of work that we've done to try and make AREDN more reliable. So it touches on a lot of software things, really. So I may go blah 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 blah, and what the hell are we talking about? So please stop me, and I will try and provide more information if I can. Okay, fine. I'd like to roam around. There's also going to be a problem. So who the hell am I? My name is Tim Wilkerson, K6 PLB. Got my license just over a year ago, and I got my license specifically to do this. Back in the COVID days, someone posted on a Reddit forum about AREDN in my local area, and I'd never heard of it until that point. And I'm like, oh, this is just totally my thing. 20 odd years ago, I did the thing that I think someone was talking about, where I got my little radio thing, and I stuck it on an antenna, and I stuck it on my house, and I pointed it at my local Starbucks so I could still use my Wi-Fi when I was having coffee down the road. And that was the first time I've messed around with antennas on my house and stuff. So when AREDN came across my view, I'm like, oh my god, this is something that's totally my thing. So I got my license, got my first node up, connected to the network in Berkeley, and very happy person. Then I made the mistake of telling people that I was retired and had time. and all was like, oh, well, they could do with some. I'm a software guy basically, and I was like, oh, they could do with some help. And the local group's like, oh, we could do with some help. So here I am. So that's where I came from, and hopefully you're in the right room. This talk is basically about fixing stuff, and broken it down into basically 3 areas of fixing things. And it kind of goes from least controversial to most controversial. And we'll talk about why as we go along. Also, as you can see on the slide, sometimes I have a really good picture that sort of helps to emphasize what the hell it is I'm talking about, and sometimes I've got nothing, right? So AI visualization is the thing now. So I stuck keywords into an AI, and it made me pictures. Very nice until you start looking at them closely, and then they turn out to be really weird. I mean, if you look at the hands on this one, the fingers are very strange. But when you first look, you think, hey, okay, and then you start looking at it like, okay, that's a bit creepy actually. Anyway, so sometimes the pictures will be useful, and I will point, and sometimes you're like, what the hell is this? It just to keep it interesting.
You're fixing that.
Are you asking questions, or is it in your...
Oh no, I was leaning, sorry.
Alright. So, weird picture. First thing we'll talk about is fixing the updates process. Now, when I first tried to update an AREDN node, and I'm sure everybody's had this experience, you go to the setting, you hit the thing you want to do, it downloads the software, it puts a page up saying, I'm updating the software, you think this is great, it's going to be better. It comes back and, oh, nothing happened.
Right.
It's exactly the same. And you think, okay, so this time I'll reboot the node and I'll do it again. No? Okay, this time I'll stand on one leg whilst I'm doing it. Maybe that's what needs to be done. I'll disconnect it from the network. I will do my nodes in alphabetical order. This is it. What I found out is that people like, I was like, well, this works for us. I do it this way, it works for us. Like, it makes no sense So one of the first things I wanted to do is like, come on, if you upgrade stuff, you want it to be reliable, and you want it to not only work, you want it to make sure it doesn't like you screw the node up when you're done. Some people have got, I'm lucky the stuff's on my roof, right? Some people have stuff on water towers which you can't easily get up. So this stuff has to work. They have to trust it's going to work. They have to know that they can just update it and it will work, and they have to know it isn't going to like screw it up in the process. So my sort of number one thing to fix was making updates work. It turned out to be quite a lot of work. We're going to talk about why and some of the choices that we made to have that happen. Fundamentally, there's not enough memory. Now, I already mentioned there are some 32 megabyte nodes out there. Those are sort of the smallest nodes that are on the mesh anymore. And we don't recommend people go out and buying them. But I am very much a believer in not making, if a ham goes and buys some hardware, they go to the trouble of putting AREDN on it, and they stick it on their roof, and they're active in the community using this stuff, I am not going to say they have to go and replace it all. I'm not going to say that our software doesn't support them anymore. We will absolutely make sure that stuff continues to work. I consider that to be incredibly important. You should never force your community to spend money, and you should never sort of try and exclude it. So fine, there's some 32 megabyte nodes out there. They're not the only ones that have problems updating, but they're definitely the hardest. And whatever we had to fix this problem, we had to fix it for them too. So what do? We don't have enough RAM to actually do this reliably, because once you've got a network going, it uses RAM, and the update uses RAM. How do you actually solve this problem? And I don't know if this is the dog. Again, it's kind of weird. So it turned out that a couple of things were going on. And one of them is that obviously a running node uses a whole bunch of memory to maintain its connections to the network, know how to get traffic through that network, and that takes some space. So what used to happen is we used to try and close as much down as we could so that we'd use less RAM. And unfortunately, we didn't do it very much. What we did was we'd shut things down, and then Linux, because Linux is trying to do the right thing, and of course Linux is at the bottom of all of this, goes, well, that all died. I'll start it all up again. And starting stuff up again is way more expensive than just having it run. So our attempt to make it better actually made it worse. There is a way of shutting stuff down, and it will stay dead. And that's what we do now. And if you shut stuff down and it stays dead, that frees up a whole bunch of memory, so that you actually have a chance to upgrade the node. And for 99 times out of 100 on a 64 meg node, that's going to do fine for you. That will work, and you'll upgrade your node, no trouble. I had a friend who manages a high site in Berkeley, and last update, he's like, that what used to take me several hours now took half an hour. So just went through all the nodes one at a time. They all worked. Nothing failed. It was great. So for 64 meg nodes, totally good. But 32 meg nodes, that doesn't work because they don't have enough memory yet. So we needed to give them more memory, and the easiest way to give them more memory was to make the update smaller, because you have to load the update into RAM. And the easiest way to make the update smaller was to remove all the Perl code. Now, for people who don't know what the hell Perl is just for people. Hopefully, some people have never had to experience Perl. Perl is a very old scripting language at this point. Still, some people still use it. My wife still uses it, which was incredibly useful during this process, because I'd be like, because I don't know Perl at all. Right? I'm like, so what the hell does this do? She's like, oh, it does this thing. So okay, fine. So, and it's, you know, it's a fine language. It's old, but it's fine. And all the AREDN sort of high level GUI codes, services codes, all written in Perl, because it sort of dates back from that time. But the language AREDN is built on a couple of layers. One is Linux at the bottom, and then the next piece up above that is something called OpenWRT. OpenWRT is a big project for routers and for wireless routers that people use in lots of different projects. Their language of choice, which is what they build their system on, is a language called Lua. Also a really old language, but not anything like as popular as Perl. It's really popular in the game world. Roblox, which some kids or grandkids may play, uses Lua to write all this sort of stuff. Anyway, they use this language as their core language, which means that it's there anyway, which means you can't get rid of it. All the libraries are there, all the stuff gets loaded into memory, it always exists. So it's there. And if we want to save memory, the easiest thing for us to do is to take all our Perl code and throw it away and rewrite it all in Lua. Because then we don't have to carry around all this Perl stuff that, when we have Lua equivalents. And Perl was half the size of the image. And not our Perl code, that's tiny. Perl libraries that we had to consume to do this was half the size of the image. And that's, if we can get rid of that, we can make our images smaller, we can get into 32 megabyte devices, and we can upgrade them. And smaller images are good for everybody, right? I mean, less memory, better, right? But, so that's what we did. We rewrote all the Perl code in Lua code. It had some side benefits. Things got a little bit faster. Using less memory when it's running. I mean, but the primary reason we did this was so that we could have reliable updates. Yeah. And at this point, I think we're at 3.22.8.0. I think we've got all the bugs out of when we made the switch, but it was a lot of stuff. So, making updates more reliable, no one really has a problem with that. Seems like a good thing to do. Next thing was fixing the network. And the first part of that is network storms. So, my first network storm was August 2021. I was sitting at my local cafe. I was going to connect into our local mesh from there using my laptop, and I connected in, and nothing was working. I'm like, what happened? And it's like, oh yeah, there's the network storm. So this was the first time I'd encountered this. Nothing new, of course, but it's the first time I'd encountered it. And okay, this seemed bad. And it turned out that the network storm problem had existed for a long time, and it had sort of restricted how big networks could be, because it had been shown, it had been understood, demonstrated, I think Orvin particularly had demonstrated this, that the bigger your network got, the more likely this was to happen. And when this happens, it just dies. Nothing can be done with it. So, okay, this is not great. We need to fix this. We need to work out why this is happening. But no one had any good data about why it was happening. People had theories, but no one had good data. And I'll come on to the theories and how they actually, once you know why it's happening, how those theories add up. But people had ideas about what could be causing it, not why it was happening. So ham I've still never met, Pascal KN6GFJ, I think he's in San Francisco. Maybe he's here, I have no idea. I've never met the guy. He did some excellent work on actually looking at what was going on in the network during the storms. And at this point, I'm going to divide the network up into two pieces. There's what users want to do on the network, look at video cameras, exchange messages, emails, whatever it is. And then there's the stuff that happens to make the network happen at all. The thing that works out how to connect nodes together, or how to send traffic through the network and so forth. And that uses something called OLSR, which is the software that we use for this. And I actually had to write it down because I don't think this is an obvious name. It's the Optimized Link State Routing protocol. And what it basically does is that every node on the network goes, here I am, this is how to find me. And that information is sent to every other node on the network. That's not an optimized way, it's not like, it's not awful in the way it does it, but it basically has to tell every other node, here I am, and then every other node goes, you're over there, I can work out how to get to you by going here, here, here. And every node does this, it's part of what it does. And what Pascal found out was that you'd see these here I am packets over and over and over and over again, just go round and round and round and round. This is not what's supposed to happen. They're supposed to go to everybody and die, right? But they just kept going round and round and round the network. So you can see in this sort of graph that isn't weird. On the left-hand side, a bunch of dots seem sort of reasonable, and then suddenly you hit this point where you've got these solid lines going across. And this is the point where suddenly we're getting these packets going round and round and round and round again, and every node is seeing the same packet all the time, and it just keeps happening, and then it just builds up, and then the network is doing nothing but sending these packets through the network all the time, and nothing else happens. This is obviously not good, but it is the first time that someone had done the work to find out why, we knew it happened, but what exactly was going on. And this was the first time we had this information. And the other sort of thing is that obviously it stops. This is happening, this is terrible. Will our network ever be the same? And then after half an hour, 45 minutes, it'll just stop. It just clears up. So, we now have some data about what was going on, but we still didn't know why they stopped, or why they end, or what we could do to stop this from happening at all. So, it turned out, if you looked at the data, that the way OLSR, that thing I spoke about that sends here I am packets around the network, understands what it's doing, and so understands what is valid data from other nodes, is by using sequence numbers. This is a pretty common networking thing. You basically number all your packets so that when someone receives them, they know that they haven't seen it before because they've never seen this number before. This one must go after this one because we've got they're in a sequence of numbers, right? But most networks also have to realize there's packet loss in there, or sometimes things turn up in the wrong order and we have to fix it, or sometimes they see something twice, so we need to get rid of it. So there's always a little bit of leniency in what they consider to be valid. So I should say at this point that this is very much how can I explain this sort of thing. So it's a little simplified from what really happens, but it covers the basic thing that happens and how we changed it. So in my little circle here, I've got 10 digits, and because packets can't have an infinite number of sequence numbers, there's some limit on them. For our example, we're going to say you can have 10, right? So a packet will get sent with 1, 0, then 1, then 2, then 3, then 4, then 5, and so on and so on. And when it gets to 9, it'll send 0 again, and that's fine because hopefully by the time you get to 9, the 0th one has long since left your network, and you're not going to get confused by anything by this cycle. So what OLSR would do is say, look, if I receive a packet, as long as it's no more than 4 bigger than the last one, I'm going to say that's fine. And that's fine because you send the packet, you get another packet, it's fine. That little imagine that sort of circle turns somewhat, so the next packet has to be within 4. So it's all, the next one will always be valid, and if it gets one that's less than it goes, never mind, throw it away. It's always going to get something. It throws it away, it doesn't retransmit it, it just transmits the stuff that it considers to be okay. But the problem here is that this assumes that everything in the network never restarts. So when a node starts up, it picks, okay, what number shall I start from? I shall pick one at random. It doesn't want to start at 0 every time, because then we just get confused from the last time it started at 0. So it wants to pick a random number. So it picks a random number, starts from there, and that's probably fine, except that when we boot a node up, OLSR will restart 2 or 3 times. So it'll start sending packets with new sequence numbers at random places 2 or 3 times. And if you get unlucky, and if you get enough nodes, you're going to get unlucky often. You can get OLSR sending out a packet that begins at 0, restart, sending a packet that begins at 4, that's okay, restart, send a packet that begins at 7, that's okay. Oh, I just got a 0, but 0 is within the window from 7, so because of the circle, and then all these packets are okay as far as everybody receiving them, and therefore they just keep going round and round the network because they're all okay, because the last one I got was also okay. And then they just go around the network all the time, and eventually they stop. The only reason they stop is because every packet has a lifetime on it. Every time it's received, lifetime is decreased. Once it gets to 0, regardless of anything else, it's thrown away. And that's the only reason these network storms ever stop. So, okay, how do we fix this? And the simplest way is we fix it by basically saying you can't have a big window of numbers, you get a little window of numbers. And that increases the probability of a storm happening goes from, once a month to, once in a couple of universe lifetimes kind of thing. I mean, basically to the point where it's just not going to happen. Yes?
How big is the sequence number? How many bits?
It's actually a 32-bit number. So you've got 65,000 sequence numbers.
You just need a better random number generator.
So no. So because the window was half the sequence numbers, it still will. Even if you pick at random, it'll still happen occasionally because the window's so big. The only way to deal with it is to shrink the window, which is what we did. And I mean, this is one of those cases where the people who wrote the software, it would work from the perspective of the experiment that they were running, because they're in control of the environment. But our environment resets and restarts all the time, and therefore it has these fluctuations that it could never envisage when they wrote the software.
It's a classic example of how software fails.
Yeah.
Like hardware.
Discover how
It will run perfectly for decades until you get into this new condition.
My favorite, and I'm sure many people's favorite thing about software is that when it fails, and you find out why it fails, and then you look at it and think, this should never really have worked. So the failure isn't the amazing part. The amazing part is it worked at all.
The rockets have blown up because of similar problems. So
Right.
Don't say that.
So there are a number of ways we could have fixed this. I will not bore you with all of them, but pretty much we wanted to find the way that is compatible with the way the network currently worked. Because remember, we could have said, for example, let's have a bigger sequence number. That'll solve the problem. But there are nodes out there running old code, and will continue to run old code. And as soon as I make the sequence number bigger, it's not compatible anymore, and stuff will break. And I consider leaving people behind is not an option. Right? You don't do that. You don't break your user base. So we needed to find a way to fix this and didn't do that, and this was the simplest way we could come up with. We also wrote some tooling because once you start, once Pascal showed the problem, it's like, okay, we obviously should be monitoring this kind of stuff, because what you can't see, what you can't measure, you can't fix, right? So there's this monitor runs on the San Francisco Bay Area mesh, and anybody can go look at this. The tool is on the mesh, but since it was designed to monitor the mesh when it was breaking, you can also get to it from the internet, because that seems slightly more useful in that moment. And it basically monitors the management traffic on the network to make sure that it's what you would expect it to be. It will text me if things look weird. You can see this is just a everyday sort of snapshot of what's going on. It's incredibly dull. Nothing interesting is happening here. But occasionally you see these little jumps when, so for example, last week somebody accidentally connected the Bay Area mesh and the South California meshes together for a while. So suddenly we had 800 nodes rather than 300 nodes. That was somewhat surprising. And this graph would jump, it would show these sudden changes. But fundamentally, since writing this and fixing the network storms, nothing's happened. It's been really dull. But that's fine, right? I mean, it's slightly irritating to have written a bunch of software to monitor something that never shows you anything interesting anymore. But on the other hand, great. The problem has definitely been fixed. Now, the last point is what actually, I mean, I've talked about what the problem was, and I've talked about how we fixed it, and it has fixed it for sure, but not about why it would ever happen. And I mentioned resetting nodes. Does it? And it does. But so does tunnels. So tunnels are super popular, and I'll say this now by saying this is no longer a problem. Tunnels are fine. Please use them. However, it used to be a problem. So Linux is great, but it's designed for certain things, and we use it in different ways, right? So we use tunnels to connect nodes together when we can't get a node into the system because there's no Wi-Fi, or when we're trying to pull in islands and stuff. And tunnels use TCP networking to connect them across the internet. Now, I don't know who chose TCP as the protocol of choice for tunnels. It was a very, very bad choice. You should not run tunnels over TCP if you can possibly avoid it. And I won't go into the I can go into the details of why it's a very bad idea, but it's a very bad idea. And in our case, it's a very bad idea because if you create a tunnel and you make a connection to another node, and then let's suppose for some other reason that network fails in the middle, let's suppose your router gets removed or something happens and that tunnel gets disconnected. TCP doesn't care. Oh yeah, half an hour. half an hour of like, well, maybe they'll come back. I'll keep all the data that you're sending on the network in this buffer for when they do. And then let's suppose they come back 29 minutes before, it gives up after 30 minutes, that's nice. 29 minutes before it's going to give up, it comes back, it goes, fantastic, you're here. I have 29 minutes worth of data for you that is 29 minutes old. Here it is. And it pumps 29 minutes worth of data into the network, including all that information, all those sequence numbers, all that routing information from 29 minutes ago. And all hell breaks loose. So, don't do that anymore. It turns out, thankfully, again, I criticize Linux, I should, it's a wonderful thing, obviously. But these are clever people. There is an option, there is a configuration option in Linux that says that TCP connection you just made, if the other side buggers off and doesn't come back, kill it. You get a minute now. it's not back in a minute, it's dead. I was quite prepared to say, damn it, 5 seconds and let's they can go. But I was a bit up to a minute. And like that seems fine. So tunnels contribute to this problem for sure. But they don't anymore. Please upgrade your software.
Are these corrections currently available in the current AREDN?
Everything I'm talking about today is in 322.8.0.
Okay.
Well, I'm really old at 319.
Yeah, you see, it makes me
That's the
sad.
problem. That's the problem.
But it also makes me want to help.
Will that 332 run in
You're not
the
back
air
in a minute.
routers and air router HPs?
C'est la vie.
Sorry?
Will that new stuff run in the air routers and the air router HPs?
If it's on the list of supported stuff, but let's talk about new highlights at the very end, shall we? Because this talk's not really about that. All right, more fixing the network. So storms, making storms go away. Again, not very controversial. That seems like a good thing. Now, link quality and link speed. Weird pictures. Right. Links can be really slow. And sometimes we know why they're really slow. They're really slow, because maybe we've got low power. Maybe there's a tree in the way. Maybe you don't have a chainsaw to fix that problem. But sometimes we don't know. I was at a site with a friend on Wednesday. Awesome SNR between the 2 points, 25 on both ends, absolutely lovely. Nothing going through in one direction, just nothing. I'm like, okay, what the hell is this, right? And in that particular case, there was a wisp on the same channel, which was unexpected because it was a hand channel. But anyway, a wisp on the same channel. We moved it and it's fine. But sometimes it's not something we can explain. The reason I got into this problem was I had just 2 nodes on my desk. I mean, literally this far apart. And I did a speed test. I thought, I should do a speed test. It was less than a megabit. And I'm like, it's this far apart? And that can't be right. What the hell is going on? So what is going on? So if you look at the AREDN website, I think we recommend a 15 dB SNR as a sort of minimum you should use between 2 nodes and consider that to be like okay. Plenty of people use 10. And I mean, sure, if it's 10 or you've got nothing, you're going to use 10, right? It's good. That's good. But AREDN itself, again, I'm going to point the finger at Linux a little bit here, although there are very particular AREDN reasons why this happens. Linux is like 3 is good. 3, yeah, 3. It's fine, that'll work, won't it? We can get a packet over there, once a day. But it's good enough, right? And it's like, well, it's not great, right? AREDN itself will try and deal with that problem somewhat. It has a measurement of link quality, which basically it's got nothing to do with how fast the link is, latency on the link, bandwidth on the link. It's all about packet loss. And for radio, that's great, right? I mean, packet loss is super important. If you got a link, looks great. In theory, should be a nice thick pipe, but like half the packets disappear. That matters, right? You should probably use a different link if you have an option. But it's not wonderful if you have a link that's doing a megabit when another link it could be doing 10 megabits, but as far as AREDN is concerned, they're the same because packet loss is 0 on both. So AREDN has issues with trying to determine the best links to use in the network anyway. Really? Go on. All right, I shall speed this up. So link quality. There is this notion of that Linux has of distance between nodes. In my little diagram here, there's a bunch of like nodes fairly close to this other node, but then there's this guy over here, super far away. We'll have these are all the same radio, no trees. His SNR is going to be less, and maybe it's super, super small. Maybe it's that 3 we were talking about. Now, unfortunately, moving this quickly forward. Unfortunately, Linux by default will go. As long as I can see someone, I will try and configure myself to speak to them. And if that person I can see has got a 3 dB thing, 35 miles from here, I can see like occasionally, it configures itself so it can talk 35 miles. And if it configures itself to talk 35 miles, it is awful at talking 2 miles. Because, speed of light. It's fast, but computers are fast. Radio is obviously, the number of bits you can get into that channel is a lot. And if you're expected to communicate with something 2 miles away, but you're like assuming it could be 35 miles away, and that packet gets lost, you're going to wait a long time before you have another go. You're going to wait a long time before you get an acknowledgement for that packet, and therefore your network bandwidth just plummets, because occasionally Linux would see a node 35 miles away and reconfigure itself to deal with that. So we had to stop doing that. By default, on any of these software, if they upgrade it, you don't get any of this stuff. It's all turned off. If you put our software in a new node, this is turned on by default. And basically, we try and work out what's the best thing to speak to by removing nodes that are super quiet, removing nodes that are too far away, and removing nodes that have too much packet loss that the radio sees rather than the software sees, and too many retransmissions. And that allows us to control how far Linux thinks it should be talking to, and that will, in every case that when we were running tests on this in Southern California, and a little bit in Northern California, every single case that we ran, it made a difference, including cases we didn't really expect it to be fair. Even links where we thought, well, this will have no effect, it should just, at best case, we would hope to be the same, which is what you want, right? Don't want to make it worse anyway. But even those, it was slightly better, but some cases it was immeasurably better, like the difference between 1 and 20.
So on that maximum distance, if you've got a link that's 2 miles apart, you don't want to set your maximum distance at 50 miles then.
Right, the maximum is set to 50 because that's a good, which we tried to come up with good defaults that wouldn't cripple people by immediately cutting them off. Mm-hmm. It won't set the distance to 50 unless there's something at 50 you want to talk to. But it says if it finds something that's 51 miles away, it will just ignore it.
But that doesn't have to do with bandwidth aggregation on that distance measurement?
I mean, it's more to do with just the way.
Is that system timing?
Yeah, it's more so. I've got no time, but it basically you send a packet at the very basic level. You send a packet and you wait for it to be acknowledged before you send the next packet, right? And the further away that is, the longer that will take. And therefore, if you don't get, so you're waiting a certain amount of time to get the acknowledgement. If you don't see it, you'll send it again. So if you get it wrong, you don't wait long enough for the acknowledgement, so you'll resend it when you don't need to, and it's too far. You're waiting too long for the acknowledgement to come back, and therefore you're waiting pointlessly when the acknowledgement gets lost. So it just impacts you back. Hello.
Yeah, these are link level acknowledgements, and on Wi-Fi, link losses are common.
Right.
There's a lot of retransmissions, but getting that time is important.
Yeah, this is all chipset configuration,
Right.
and it would be lovely if I could configure it per device, but you get one. So, all right, we're going to do this really fast. So the last piece, and probably the most controversial piece, is names and services. we've all had the experience of nodes on the mesh that don't actually exist anymore, services that you click on that don't resolve to anything. So the most recent stuff we've been doing is to try to clear out the stuff that simply isn't really there anymore. It's a full user experience. And this is one that I think I would say is still a work in progress a little bit. I have concentrated on the consumer experience, if you like. That is, the person looking at the mesh, looking for things to try, clicking on a link, having it work. I have not concentrated on the other poor sod on the other side who's trying to configure this. And if I skipped a couple of slides, you'll see what I mean. OLSR, bless it, remembers every single thing that's ever seen on the mesh, pretty much until you reboot it. So if you ever had a node on the mesh, it's going to stay there forever. If you change its name, it'll remember all the names it ever had. If you publish a service, it'll remember that service, even if you don't have that service anymore. So we needed to make some changes to OLSR so it would forget stuff. That was the first thing we had to do. It can forget things. So if somebody stopped publishing a service, it would forget it. If a node went away, it would forget it. If a node changed its name, it would remember the new name, but it would forget the old name. So that was the first step in this. That's not too controversial. It's like, let's forget things that aren't there anymore. Seems kind of good. I'm going to skip over how that happens and talk about service validation. So I did this. I noticed I'd done this myself just before I came down to this conference, where we'll publish a service on our node, and then maybe it's mesh chat is a classic way. Somebody installs mesh chat on their node, they upgrade their node, all the packages go away because that's what happens when you upgrade a node. But that URL that you're publishing for mesh chat, it's still there, saying I have mesh chat, and you don't because you didn't reinstall it because you forgot, like I did. So what we wanted to do was to stop publishing things that aren't really there. So now, once an hour, a node will look at all the things you've published, and it will actually do its best to make sure that they exist. Is it a web page? Can I pull the web page? Is it like an NTP server? Can I at least talk to the port that's published on? Does the host name actually exist, or did that pie fall off the network at some point? And if they're not actually, if we can't reach them, we won't publish them. We don't delete them or anything. They're still in your configuration, but we won't publish them anymore. And that's I think, a great consumer experience because as somebody browsing the mesh, I don't see links to things that aren't there. However, as I knew this but discovered it myself, see that I put a little, you get a little thing on your page saying, hey, this service isn't published. And yes, sure. And how many people go to their ports page on a regular occurrence to check these things? I mean, no one does that, right? Why would you do that? Okay, Matheson does that. So I think a good consumer experience because you stop trying to use stuff on the mesh that doesn't exist. It doesn't seem broken, but I need a better configuration experience because if something isn't working, I need to let people know that rather than expect them to just stumble across it at some point. So, work in progress here. Conclusions. We spent the last year trying to make the mesh better in a bunch of ways. Trying to make it easier to update, trying to make it more reliable, better throughput, and trying to make the services that actually people are publishing either really be there when you click on those links. But I mean, there's more to do. There's always more to do. But there is one sort of piece of feedback I've had, and it's like, does this make this too complicated? One of the sort of goals of AREDN's mesh has always been simplicity. We don't want you to be I might be into the whole networking thing, but we don't want people to have to be, interested in networking as a profession, to put a node on their house, point it into a mesh, and join the community, right? And some of these changes, although we've tried to make them as automated as possible, try to put good default values in as we possibly can, definitely give the ham more configuration options, more knobs to play with, and arguably therefore make it more difficult to configure stuff. The flip side of that argument is, well, we're not idiots, are we? I don't think we are. Therefore, giving people control over their radios is not a bad thing, as long as we let people know what the knobs do. So, that's not too bad.
Right on
I
time.
blame all for stealing my time, apart from that.